Alright everybody, in this video let's try to implement the remove functionality on a singly linked list. So what exactly this remove operation does on a singly linked list is basically it is used for removing the node at a given position that is requested by the user. To give a specific definition as part of this remove implementation, what exactly we will do is we will basically take the index from the user and we will basically go to this index and whatever the node that we have at that particular index, and we will simply try to remove that node, and in the end we will simply return that node back to the user as a output. Okay, so that is the ultimate functionality of a remove operation on a singly linked list. Here obviously we are taking the index from the user, right? So obviously there would be two cases. The first case is the valid index and the second case is invalid index. Here if you observe the singly linked list that we have, right, we know the valid values of index on a singly linked list will basically start from 0 and will end at length of the singly linked list minus 1. So for the remove operation, the valid range of the indexes will be from 0 till the length of the linked list minus 1. That means in the singly linked list that we have here, right, the indexes will be at 0, 1, 2, 3, 4 and 5. If user passes any of these indexes, we will be able to delete that node and we will be able to return the value. And one thing that you have to make sure here is whatever the head node and tail node and whatever the length that we are maintaining on the singly linked list, right, we have to make sure that those values are still consistent even after deleting the node from the singly linked list. That is something that that we have to remember. Now let's just try to understand whatever the different cases that can come when we are trying to implement the remove operation on a singly linked list. The very first scenario is basically, since we are taking the index from the user, right, first check would be to check if the index that user is passing is invalid. So that is the first check. When we will say the index is invalid, if the index is less than 0 or if the index that is given by the user is greater than or equal to the length of the linked list. If user passes the index that falls into this range, we will simply return null or none based on our programming language that we are using for implementation. If we are using Python based implementation, we will return none. Okay, so that is the first scenario. And the second scenario is obviously a valid index that is given by the user. So in the valid index also, what exactly we will do is we will try to reuse some of the functionalities that we have already implemented. So if you remember the previous implementations that we have done it, right, in those cases, basically when we spoke about those functionalities, specifically when we spoke about the pop functionality and the shift functionality, pop functionality is basically used for deleting the very last node we have in the singly linked list, and the shift operation is basically used for deleting the very first node we have on the singly linked list. So whenever the user is passing the valid index, we can reuse this push and pop shift functionalities. So how will we make use of that is, inside the valid index scenario, as part of the first check, what we will do is, if the index that is given by the user is 0, we will check. If it is 0, right, what exactly we need to do? We need to delete the head node, right? We have to delete this head node. That means whatever the next node that we have inside the singly linked list, that should become the new head of the singly linked list. That's why here this operation is nothing but the shift operation. So we will simply call the shift operation with whatever the index or 0 itself we can pass, because whatever the index that user is passing is 0. In the end, this shift function automatically returns the node that it is deleting, right? And we can return that node itself. Okay, so that is the first scenario. And the second scenario is basically if the index that is passed by the user is equal to the very last we have very last index we have on the singly linked list. That is, if the index is equal to the length of the singly linked list minus 1, and we are anyway maintaining the length in our singly linked list, right? And we will be able to get that length directly, and we will be able to compare it very easily as well. So if it is matching this case, that is nothing but we are trying to delete the very last node we have on the singly linked list. That operation is nothing but pop operation. So we will simply call the pop operation directly. Okay, and I forgot to mention, when we perform the shift operation also, we will not pass any index as an argument, right? Because shift operation itself will basically delete the very first node. So it automatically knows that it has to delete the current head node which is at index 0. So this is a small change. By mistakenly I have written index as a function argument. Okay, now the third scenario in the valid case is basically if the user passes any index from 1 till the last but 1th index. In that case, what we have to do is we have to make sure that we are deleting the node at the index that is given by the user. And now I will explain you what exactly is the algorithm that we follow. Now here, let's assume that the singly linked list that we are using for performing the remove operation contains, let's say, some 5 values or 5 nodes in it, and we have the head node and we have the tail node, and these will have some values like 1 2 3 4 5 or some other random values they will contain, right? And the indexes will be 0 1 2 3 4. Now we have already understood when the user passes the index 0 and when the user passes index 4, we have already handled those scenarios. Now our worry is if the user passes an index from 1 to 3, right? Now let's assume that in our implementation the index that is given by the user is 2. So we have to delete this node with the value 3 because it is at index 2. Now to delete this node, what we have to do, we have to make sure that whatever the next pointers that we are keeping track of in each and every node, we have to make sure that we are deleting that. So to do that, what exactly we will do is, first we will get the node that is at whatever the index that is given by the user minus 1th position. So in our case, the index that user has given is 2. So we will go ahead and get the node at the index 1th position because we are trying to get the node at index minus 1th position, because index minus 1th node will contain the next or the reference of the node that is at the indexed position in the next variable of that particular node, right? So we have to make sure that that node we are updating it to the next of the node that is at indexed position. So what exactly we will do, we will get the node that is at index minus 1th position and we will update the next of that particular node with the next of the node available at indexed position. That means that this node's next will be having the value of or the reference of the node 4. In that way, this node is actually getting deleted. Okay, I hope you understood. What exactly we will do is, first we will go ahead and we will try to get the node that is at index minus 1th position, because in that node we have the reference of the node that is at indexed position. So what we will do, we will simply update that next variable or that next value with the next of the node that is at indexed position. So that is the third scenario where index is greater than 0 and less than length of the singly linked list minus 1. That means that the very last index that we have. Now that we have completed the insert operation and we have discussed the algorithm and pseudocode behind the remove operation, let's just write the C++ logic for the same thing. So here, after removing the node at the given index by the user, we need to return the node that we have deleted back to user. So the return type of the function will be node, and let's name the function as remove, and this function will basically take the index, basically the position at which the node needs to be deleted. Okay, so here the remove operation is also taking the index, right? That means that it should be a valid index. Any non-valid index should be not honored. We should basically return null or something back to the user. So what is the valid index range for this remove operation, right? So anyway, the indexes that we have on the singly linked list are also of similar type to what we have on the arrays. So indexes are basically starting from 0 and ends at length of the linked list -1. So if we need to remove the node at that specific index, these are the allowed values. So any index above that doesn't fall into this range are basically invalid indexes. So let's just write that first check now. So if the index given by the user is less than 0, or if the index given by the user is greater than or equal to the length of the linked list that we have, it is an invalid index. So we will simply return null back to the user. Okay, so that is the first case. Now we will try to reuse a couple of the functions that we have already implemented based on the index that user is passing. So if at all, if the index given by the user is equal to 0, that means at index 0 we have the head node, right? And by passing the index 0, user wants to delete that head node, which is nothing but shift operation. That is something that we have already implemented. So what we can do is we can simply call the shift operation, and this shift operation already deletes the very first node. That means the node at index 0, and will return the node back to the user, right? So we can simply return whatever the shift function is returning. Okay, as part of the third scenario, if at all the index that is given by the user is equal to the last index that we have on the singly linked list, that means the length of the singly linked list -1. In this case, user wants to delete the very last node, that means the tail node. That is nothing but pop operation that we have already implemented, and this pop operation also deletes the node, very last node, and it will return that, right? So we can simply return that itself here. Okay, so we have successfully handled the three scenarios where invalid index and the node that user wants to delete is at index 0, and the node that user wants to delete at the very last index, that is nothing but tail node. If user passes any other index, we need to write the logic for that right now. So first of all, if at all, if we want to delete the node at this particular index, first we need to get the node before this index, and we need to get the nodes after this index, such that nodes before this index can be connected with the nodes after this index. Okay, that's the reason why first let's try to get those nodes such that we can delete the node at this specific index position. So let me just write the logic, and first I want to get the nodes that are at this index -1th position. So let me just let me just name them as node, and for this let me just reuse the get functionality, and let's just pass the index -1th position. If the user passes an invalid index, like we have discussed in the case of insert also, we don't have to worry about the invalid indexes being passed to the get function from the remove function here, because if at all user passes an invalid index, that will be handled by this if condition only. If at all, if the index is valid one, then only the logic will come on to this get function. Okay, now anyway, here we will have a valid node that is available at this index -1th position. Now let me just read the node at this indexed position. So let's just name node at indexed. Okay, or we can simply say node at index is equal to, this is node at index -1th position, right? If we simply read the next of this, we will simply have the indexed node. So we can simply do node dot next. Now we also need the nodes after this nodes that is at indexed position. So for getting the nodes after the indexed position, we can read the next of the node at index. So let me just read that. Let's just name them as next nodes, and this will be node at index dot next. Okay, now to delete the node at this index thread, what we can do, we can simply do node dot node dot means basically the node at index minus 1th positions. That next will be pointing to the nodes from index plus 1th position, which is nothing but next nodes. So all we have to do here is node dot next is equal to next nodes. That's it. By doing so, we have deleted the node at that specific index position. As we have deleted one node, we need to decrement the length by 1. Okay, and in the end we need to return the node that we have deleted, right, which is nothing but this node at index. Okay, so that is the way we implement the remove operation to delete the node at given index by the user, honoring all the cases not to mention. Okay, now let's just try to validate this in our main function calls. So here let me just comment out this insert and let me just call the remove, and let's just try to test some invalid scenarios. And let's just say the index that I have passed is minus 10. Since it is a negative value, obviously it is an invalid index, so I should basically not see any difference at all in the resulting single linked list. So before remove and after remove, the linked list is same, there is no change at all. And let's test the index which is invalid in terms of positive number, and that also the same thing, you should not see any change at all on the console. Okay, it is exactly same. Now let's just test the valid scenarios. Let's just say I want to delete the node at index 0th position. That means whatever the value we have at index 0, which is 0, that needs to be deleted. So the resulting linked list will have 10 and minus 10, and 10 will be the head node and minus 10 will be the tail node of the singly linked list. So if I run this now, see, after performing the remove, the resulting linked list has 10 and minus 10 only. Okay, so that is one valid scenario. Let's just try to test by passing the index 1. Index 1 has 10, right? This needs to be deleted. As a result, 0 and minus 10 should be printed on the console. So if I execute this now, see, 0 and minus 10 is something that we have printed. Now let's just say there are no values at all on the singly linked list and I have passed index 0. So if I execute this now, obviously there are no values, right? Even remove function does nothing because it will go into this shift call, and shift call we have already handled the logic for all the scenarios, right? Here if the length is 0, we are simply returning head node, which is nothing but null itself. So that has been handled anyway. So as a result, we have printed 2 empty strings as part of this first traverse and second traverse. Okay, so that is how we implement and validate the remove operation on a single linked list, honoring all the scenarios. Okay, I hope you understand it. Insert operation and remove operation are little bit tricky because we are trying to honor, there are more number of cases that we need to honor, right? That's the reason why it seems little tricky, but if you understand the singly linked list core concept, you will be able to understand the insert and remove operation as well. All we have to worry is adjusting the next connections appropriately such that we will not have any abnormalities in the singly linked list that we are keeping track of. Alright, now that we have implemented the remove functionality on a singly linked list, let's go ahead and let's try to understand the time complexity and space complexity involved in this specific operation. So just like any other operation, likewise how we have discussed, let's just try to understand it in terms of both best case scenario and in the worst case scenario. So here, when will the best case scenario of the remove operation will actually occur? Whenever we are trying to remove the very first node on the singly linked list. That means we have certain number of nodes available on our singly linked list and we are trying to perform the remove operation of a head node. That means that we are reusing the shift functionality, right? When the user passes the index 0, we are deleting the head node itself. Obviously, we know shift function will automatically take constant amount of time. So in the best case scenario, the time complexity of remove operation is order of 1, which will basically occur when we are trying to delete the head node of a singly linked list. Okay, when will the worst scenario of the time complexity will actually occur? Whenever we are trying to delete the very last node on a singly linked list. That is nothing but the we reused pop operation, right? What exactly pop operation had to do? It has to go to last but one node and it has to update the next of last but one node to null, right? That's why we have to run a loop for n number of times to reach the last but one node. As a result, in the worst case scenario where we are trying to delete the very last node we have on a singly linked list, the time complexity will be order of n, which is nothing but the time complexity of the pop operation. Okay, that is how time complexity and space complexity are calculated in terms of best case and in terms of worst case scenario. Now let's go ahead and let's just try to understand the space complexity of the algorithm that we are writing. Obviously, in the best case, we are reusing the shift operation where we are trying to delete the very first node on a single linked list. In that case also, we simply, we will not do anything. We will simply take one variable like current head and we will simply update the head node to the next node by using that simple current node or some other temporary variable. As a result, in the best case scenario, the space complexity will be order of 1 only. Okay, so in the worst case scenario, yeah, we will run a loop for n minus 1 number of times to reach the last but one node, but we will go to that node with the help of a simple variable called current node. If you remember the pop operation, right, we have taken the help of a current node. Using that current node itself gets updated with the subsequent next nodes as we progress further onto the singly linked list till we reach a point where we are at the node that is at index minus 1th position. As a result, even though we are running the loop for n number of times, we are reusing a simple single variable like current head or some other temporary variable. Okay, as a result, in the worst case scenario also, the space complexity will still remain order of 1 only in terms of performing the remove operation as well. Okay, so that is the time complexity and space complexity analysis of a remove operation on a singly linked list. Okay,